Welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 1585, titled Check if string is transformable with substring sort operations. In this problem, we aim to determine whether we can transform one string into another using a series of substring sort operations. We'll break down the problem, identify the key challenges, and explore an efficient approach to solve it. Let's get started. In this problem, you are given two strings, s and t, both of the same length and composed of digits from 0 to 9. The goal is to determine if it is possible to transform string s into string t by repeatedly performing a specific operation. The operation allows you to choose any non-empty substring within s and sort it in non-decreasing order. You can perform this operation as many times as needed. If s can be transformed into t through this process, you return true. Otherwise, you return false. For example, if s is 84,532 and t is 34,852, the output is true because it is possible to transform s into t using the defined operation. Now, let's explore what this transformation looks like in detail. To understand how the transformation works, consider the first example where s is 84,532 and t is 34,852. To transform s into t, you can start by selecting the substring 4. Sorting it doesn't change s, so it remains 84,532. Next, choose the substring 853 and sort it. This results in 34,852, which matches t. Since we successfully transformed s into t, the output is true. On the other hand, let's look at the second example. If s is 34,521 and t is 23,415, no sequence of sorting any substrings in s can produce t. This makes the transformation impossible, so the output is false. These examples highlight how the feasibility of transformation depends on the ability to rearrange digits within substrings to match the target string. Now, take the third example where s is 12,345 and t is also 12,345. Here, the strings are already identical, so no operations are needed. The output is simply true. This demonstrates that when s and t are equal from the start, the transformation is always possible. Additionally, the problem comes with certain constraints. Both strings must have the same length, which can be as large as 100,000 characters. Furthermore, s and t are strictly composed of digits from 0 to 9. These constraints mean the solution needs to be efficient enough to handle very large inputs while adhering to the rules of the operation. Let's break down the operation and key observations that can help us solve the problem. The operation allows sorting a single substring at a time, meaning you can change the relative order of digits within that substring. However, you cannot directly swap digits that belong to disjoint substrings. One key observation is that the relative order of digits in s must allow for the exact order required by t to be achieved through substring sorting. If any digit in t is out of order compared to its position in s and cannot be brought closer by sorting a substring, the transformation is impossible. Some edge cases to consider include when s equals t initially, which always results in true. If there are digits in one string that don't exist in the other, transformation is outright impossible. The large input size constraint also means the solution must be optimized. Using data structures like queues or arrays to track the positions of digits in s and compare them to t can help achieve this efficiency. An efficient algorithm will ensure the solution runs within acceptable time limits for all valid inputs. To approach this problem, we need to determine whether it's possible to transform string s into string t using a specific operation, selecting a substring in s and sorting it. The constraints of the problem require us to handle this carefully to ensure correctness and efficiency. Let's start by considering a brute force approach. The idea here is to simulate all possible substring sort operations. At each step, we check whether sorting a specific substring brings s closer to matching t. For this, we would begin with s and, for each character in t, locate the next occurrence in s and verify if it can be moved into its correct position by sorting a substring. However, this method has a significant drawback. The time complexity is exponential because of the vast number of possible substring sort operations. This makes it impractical for longer strings, as it doesn't leverage the structure of the problem efficiently. While conceptually straightforward, this approach is far too slow for real-world use cases involving large inputs. To address the inefficiency of the brute force approach, we turn to an optimized strategy that uses a greedy method combined with position tracking. The first key observation here is that the digits in S must appear in the same relative order as in T. This means that both strings must have identical frequencies of each digit, and the order of digits in S must respect the order in T. The second observation is that when transforming S to T, each digit in S must move to its position in T without disrupting the relative order of smaller digits to its left. With these insights, we can simulate the transformation process without explicitly sorting substrings. Instead, we track the positions of each digit in S using a queue for each digit from 0 to 9. Then, as we iterate through each digit in T, we check if the current digit can be pulled forward in S while ensuring that no smaller digits block its movement. If this condition is met, we remove the digit from its queue, otherwise, the transformation is deemed impossible. This approach is efficient because building the queues takes linear time, and processing each digit in T is constant on average. Thus, the overall complexity is O(n), making this method both elegant and well-suited to the problem's constraints. The optimized approach with position tracking stands out as the most practical strategy for this problem. Its linear time complexity, O(n), ensures that it can handle large inputs efficiently. Unlike the brute force method, which is computationally infeasible due to its exponential complexity, this approach is designed to directly address the problem's constraints in a scalable manner. Additionally, while the optimized approach is slightly more complex to implement, it is highly intuitive once the key observations about digit order and movement are understood. By leveraging queues and focusing on the relative order of digits, it avoids unnecessary operations and provides an elegant solution. In summary, the greedy approach with position tracking is the chosen strategy because it balances efficiency, clarity, and alignment with the problem requirements, offering a robust and scalable solution for transforming S into T. To solve this problem, we need to determine if we can transform string S into string T by repeatedly selecting any substring of S and sorting it. Both S and T are permutations of digits from 0 to 9, and their lengths are the same. The primary challenge lies in efficiently verifying if this transformation is possible under the given constraints. First, we can observe that since both strings are permutations, their character counts must match. If the frequency of any digit differs between S and T, the transformation is immediately impossible, and we return false. Now, the main insight is that while substrings can be sorted, the relative order of characters in S must allow us to reach the relative order required by T. Specifically, for a digit D in T, any smaller digits that appear earlier in S must have already been placed into their correct positions in T before we can place D. This ensures that the sorting operations do not violate the relative order constraints. To implement this, we use an array of queues to track the positions of each digit in S. For each digit D from 0 to 9, we maintain a queue that stores the indices where D appears in S. This allows us to efficiently check and update the positions of digits as we simulate the transformation. Let's break this down into steps. First, we initialize an array of queues called digit_positions, where each queue corresponds to a digit and stores its indices in S. For example, if S is 84,532, the positions of 2, 3, 4, 5, and 8 are stored in their respective queues. Next, we iterate through each digit in T. For each digit D, we check the index of its first occurrence in S using digit_positions, D. Before placing D, we ensure that no smaller digits, from 0 to D1, appear earlier in S. This is done by examining the front of the queues for all smaller digits. If this condition holds, we remove the first occurrence of D from its queue and proceed. If not, the transformation is invalid, and we return false. If we successfully process all digits in T, the transformation is possible, and we return true. Let's work through an example to see the algorithm in action. Suppose S is 84,532 and T is 34,852. First, we initialize digit_positions, which stores the indices of each digit in S. For instance, digit_positions 2 holds 4, digit_positions 3 holds 3, digit_positions 4 holds 1, and so on. Now, we process each digit in T. Starting with T, 0 equals 3, the first occurrence of 3 in S is at index 3. There are no smaller digits, like 0, 1, or 2, appearing before index 3 in S, so we can place 3 and remove it from the queue. Next, we process t, 1 equals 4. The first occurrence of 4 in S is at index 1, and again, no smaller digits appear before this index, so we place 4. Following this logic, we process 8, 5, and finally 2. Since all digits in T satisfy the placement constraints, the transformation is possible, and we return true. This algorithm highlights several key insights. The transformation is only feasible if the relative order of digits in S allows us to sort substrings to match T. By using queues, we can efficiently track digit positions and enforce the relative order constraints without explicitly sorting substrings. The use of an array of queues allows us to access and update digit positions in constant time for each digit. In terms of complexity, building the digit underscore positions array requires O(n) time, where n is the length of S. Processing each digit in T involves checking at most 10 queues, one for each digit from 0 to 9, which also takes O(n) time overall. Therefore, the algorithm runs in O(n) time, making it highly efficient for this problem. When implementing this algorithm, it's important to handle edge cases carefully. For instance, if the digit frequencies in S and T don't match, we can immediately return false without further computation. If either S or T is empty, the transformation is trivially possible, and we return true. Additionally, repeated digits must be processed in the correct order, ensuring that indices are handled sequentially. To optimize further, we can terminate early if a digit placement fails, saving unnecessary computation. We can also skip checking queues for digits that don't appear in S, minimizing redundant operations. These considerations help ensure the algorithm is both robust and efficient. This solution begins by leveraging a dictionary POS, where each key represents a digit, 0 to 9, and the value is a deque storing all the indices of occurrences of that digit in the string S. This allows for efficient tracking of the positions of each digit. Next, we populate the POS dictionary by iterating through the string S and appending the index of each digit to its corresponding deque. This pre-processing step ensures we can efficiently retrieve and remove the earliest occurrence of any digit. We then iterate through the string T. For each character in T, we convert it to an integer digit. If there are no remaining indices for this digit in S, checked via POS digit, it means the transformation is impossible, so we return false. If the digit is present, we retrieve and remove its earliest index from the deque using popleft. This represents using the earliest occurrence of this digit in S to match the current character in T. Before finalizing this match, we check if any smaller digit, 0 to digit 1, has an index earlier than current underscore POS in S. If such a smaller digit exists, it implies that S cannot be transformed to T since the smaller digit would block the sorting operation needed to bring the current digit to its position. In this case, we return false. If no blocking smaller digit is found, we continue processing the next character in T. If we successfully process all characters in T, it means the transformation is possible, and we return true. This approach is efficient, as each index is visited and processed exactly once. The overall time complexity is O(n), where n is the length of the strings S and T. Here, we begin by importing the necessary utilities and defining the solution class along with the isTransformable method. The goal of this method is to determine whether the string S can be transformed into the string T using a specific set of substring sort operations. First, we create a map that stores the positions of each digit, from 0 to 9, in S. This is achieved using a hash map where the keys represent the digits, and the values are deques that will hold the indices of each digit in S. Next, we iterate over the string S and populate this map by mapping each digit to its respective positions. This allows us to keep track of where each digit appears in S. After that, we start processing the string T. For each character in T, we determine its numeric value and check if there are any occurrences of that digit left in S. If not, we return false, as it means T cannot be formed from S. Otherwise, we retrieve the earliest position of this digit in S by polling its deque. Now that we have the earliest position of the current digit in S, we need to ensure that the transformation respects the sorting constraint. Specifically, we check if any smaller digit, one with numeric values less than the current digit, appears before the current position in S. To do this, we iterate through all smaller digits and examine their deques in the map. If any of these smaller digits have a position that is less than the current position, it means the transformation would violate the order, so we return false. If no such condition is encountered, we proceed to the next digit in T. Once all characters in T are processed without issues, we return true, indicating that S can indeed be transformed into T using the specified operations. This approach ensures that the transformation is both efficient and respects all constraints of the problem. To solve this problem, we start by initializing the necessary data structures. Specifically, we create a dictionary called POS where each key represents a digit from 0 to 9, and the value is a deque that will store the positions of that digit in the string S. For the example where S equals 84532 and T equals 34852, after processing S, the POS dictionary is populated as shown. For instance, the digit 8 is at index 0, 4 is at index 1, and so on. Next, we begin processing each character of T. Starting with T, 0 equals 3, we check if the deque for the digit 3 in POS is empty. Since it's not, we pop the leftmost index, which is 3. Then, we verify that no smaller digit, like 0, 1, or 2, has an earlier index than 3 in POS. This condition is satisfied, allowing us to continue. The state of POS is updated accordingly. Now, we move to the next character in T, which is T, 1 equals 4. Here, the digit is 4, and we pop the leftmost index from POS, 4, resulting in current_POS equals 1. We then check all smaller digits, from 0 to 3, to ensure none of them have earlier indices in POS. Since this condition holds true, we proceed. The updated state of POS reflects that the index for digit 4 has been removed. Next, we process the remaining characters in T, T2 equals 8, T3 equals 5, and finally T4 equals 2. For each digit, we perform similar checks. All conditions are satisfied, and every character in T is successfully processed. Therefore, the output for this example is true, meaning T can be transformed from S using the substring sort operations. Let's consider another example where S equals 1 2 3 4 5 and T equals 3 1 2 4 5. First, we initialize the POS dictionary by processing the string S. Each digit is mapped to a deque containing its index in S. For instance, 1 is at index 0, 2 is at index 1, and so on. With this setup, we start processing the string T. For T, 0 equals 3, the digit is 3, and the leftmost index in POS, 3, is popped, giving us current_POS equals 2. We then check if any smaller digits, like 0, 1, or 2, have earlier indices in POS. Since all conditions are met, we proceed. Next, for T, 1 equals 1, the digit is 1, and its current_POS is 0 after popping from POS, 1. Again, no smaller digits have earlier indices, so we continue. After this, we process T, 2 equals 2, repeating similar checks. For the digit T, 2 equals 2, we pop the leftmost index from POS, 2, resulting in current_POS equals 1. This satisfies all the necessary conditions for smaller digits. We then continue processing T, 3 equals 4 and T, 4 equals 5 in sequence, verifying that each digit can be processed without violating the constraints. By the end, all characters in T are processed successfully, and the POS dictionary reflects that all indices have been used. The output for this example is true, confirming that T is transformable from S. Now, we move to the next example, where the strings demonstrate a different scenario. For the example where S equals 1 2 3 4 5 and T equals 5 4 3 2 1, we start by initializing the POS dictionary once again. After processing S, each digit maps to a deque containing its index. For instance, 5 is at index 4, 4 is at index 3, and so on. We then begin processing T. The first character, T0 equals 5, has a current_POS of 4 after popping from POS 5. Since no smaller digits have earlier indices, we proceed. Next, T1 equals 4 is processed with a current_POS of 3, and the same conditions are satisfied. For T2 equals 3, we pop its index, validate the conditions, and continue for T3 equals 2 and T4 4 equals 1. All checks pass, and the output is true, confirming that t is transformable from S in this case as well. To analyze the time complexity of this solution, we start by breaking down the key components of the algorithm. First, during the initialization phase, we create a dictionary called POS that maps each digit from 0 to 9 to an empty deque. Since the size of the dictionary is fixed at 10 keys, this initialization step has a constant time complexity of 1. Next, we populate the POS dictionary by iterating over the string S, which has a length of n. For each character in S, we append its index to the corresponding deque in POS. Since the loop runs n times and the append operation for a deque is 1, this step contributes n to the overall time complexity. Now, let's consider the steps involved in processing the string t. For each character in t, which also has a length of n, we perform two key operations. First, we access and remove the smallest index for the current digit by using the popleft operation on the corresponding deque in POS. This operation is highly efficient and takes 1 time. Second, we check for smaller digits to ensure that the transformation constraints are satisfied. For this, we iterate through the deques of all smaller digits, from 0 to the current digit -1. While this might seem expensive at first glance, each index in these deques is processed and removed only once during the entire algorithm. By using amortized analysis, we can conclude that the total cost of these checks across all iterations is n. Therefore, when we combine these steps, the overall time complexity of the algorithm is n. Next, we analyze the space complexity of the algorithm. The main contributor to space usage is the POS dictionary, which holds 10 deques, one for each digit from 0 to 9. In the worst-case scenario, all indices of the string S up to n indices could be stored across these deques. As a result, the space required for the POS dictionary is n. Aside from this, the algorithm uses a few auxiliary variables such as digit, char, and current_POS for iteration and temporary storage, but these variables require only constant space, or 1. Therefore, the overall space complexity is n, with the POS dictionary being the dominant factor. We can also evaluate the algorithm's performance in different scenarios. In the best-case scenario, where S and T are identical, the algorithm simply iterates through T and pops indices without needing to check smaller digits. This results in a time complexity of n. In the average case, the algorithm performs as described, processing indices and performing necessary checks, which still results in n time complexity. Even in the worst case, such as when S is sorted in descending order and T is sorted in ascending order, the algorithm maintains its n time complexity due to the amortized efficiency of deque operations. When compared to brute force approaches, which might involve generating all possible permutations of S and checking for a match with T, this solution is far superior. A brute force approach would have a factorial time complexity of n due to the sheer number of permutations, whereas our solution achieves linear time complexity by leveraging the properties of deques and digit constraints. Finally, let's solidify our understanding of the algorithm's time complexity with a mathematical proof. Each index in the string S is appended to a deque exactly once and is also popped from the deque exactly once. This results in n total operations for deque management. Additionally, each index is checked at most once during the smaller digit validation step, which again contributes an amortized n cost. Combining these observations, the overall time complexity of the algorithm is n. As for space complexity, the POS dictionary stores all indices of S across 10 deques, requiring n space in the worst case. The algorithm is therefore both time and space optimal for this problem, achieving the best possible efficiency under the given constraints. Let's go over some common mistakes to watch out for in this problem. First, it's important not to ignore the sorting constraint. You can't just sort any substring arbitrarily to match the target string T. The order of numbers in S must respect the sequence in which they first appear in T. For instance, if T requires the digit 3 to appear before 2, but in S, 3 comes after 2, then transforming S into T would be impossible. Always validate this relative ordering. Next, avoid using inefficient sorting approaches. Repeatedly sorting substrings can lead to high time complexity, often n², or worse. Instead, you should use a more efficient tracking mechanism, such as queues or arrays, to monitor the positions of digits from 0 to 9. Another common pitfall is mishandling out-of-order indices. When you're checking if a digit D in S can be moved to its position in T, you need to ensure that no smaller digits, which should appear earlier, are blocked behind D. Lastly, be mindful of edge cases. These include scenarios like empty strings, strings with duplicate digits, or situations where S and T are already identical. Missing these edge cases can lead to an incorrect or incomplete solution. Another issue to be cautious about is mismanaging data structures. If you're using a regular list instead of a deque for queue-like operations, you might introduce unnecessary inefficiencies. Choosing the right data structure can greatly simplify your implementation and improve performance. From an interview perspective, understanding the constraints is key. You want to clearly demonstrate how you maintain the relative order of smaller digits while solving the problem. Interviewers often evaluate your ability to apply these constraints effectively. Additionally, highlight your use of optimal data structures, such as arrays or queues, to track the indices of digits from 0 to 9. This approach helps you achieve the desired linear time complexity. If you discuss alternative methods, be sure to articulate why brute force sorting is not efficient and how the optimal solution avoids redundant operations. Finally, always test your algorithm against a variety of edge cases. For example, when S equals T, no transformation is needed, while S equals 321 and T equals 123 requires a complete reordering. Another challenging scenario is when strings contain duplicate digits, such as S equals 1123 and T equals 1231. Checking these cases ensures your solution is robust. This problem also shares similarities with other string-related problems, which can help you build transferable skills. For example, in LeetCode 792, number of matching subsequences, you use similar index tracking techniques to verify if certain subsequences exist in a string. LeetCode 316, remove duplicate letters, involves maintaining the relative order of characters while ensuring specific constraints, which parallels the logic here. Another related problem is LeetCode 2186, minimum number of steps to make two strings anagram 2, which focuses on transforming one string into another through specific operations. While not directly related, LeetCode 56, merge intervals, reinforces ideas around ordering and interval management, which can also be useful in understanding how to address constraints systematically. Exploring these problems can deepen your understanding of the patterns and approaches relevant to string manipulation challenges. Finally, let's compare a few alternative approaches to solving this problem. One option is brute forcing the solution by sorting every possible substring to see if the target string T can be formed. While this method is simple to implement, its exponential time complexity makes it impractical for larger inputs, especially when n exceeds 10. A more efficient approach is a greedy strategy with index tracking. Here, you use arrays or queues to store the positions of each digit in S. For every digit in T, you check if it can be moved to its desired position without disrupting the order of smaller digits. This method achieves O(n) complexity but requires careful implementation to avoid mistakes. For more advanced cases, you could use data structures like segment trees or Fenwick trees. These allow you to handle range queries and updates dynamically, which can be useful for managing constraints. However, while this approach is highly efficient, it adds significant complexity to the implementation and may be overkill for this particular problem. Choosing the right approach depends on balancing efficiency with implementation simplicity. Thank you for following along as we tackled LeetCode problem number 1585. To recap, we explored how to determine if we can transform one string into another using substring sort operations. This problem served as an excellent opportunity to practice working with constraints and efficient data structures. If you found this helpful, be sure to like, comment, and subscribe for more content like this. Thanks again, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!